The human mind evolved to survive on a narrow stage, a world measured in steps in horizons in distances you can cross within a day. We are remarkably good at this scale. We can judge the size of a room at a glance. We instinctively feel the weight of a mountain, the span of an ocean, the height of the sky above us. But the universe does not operate on this stage. The moment distances stretch beyond daily experience, intuition begins to fail. Not gradually, not politely, it collapses. When we hear that the Earth is large, we imagine continents and storms and curved horizons. When we hear that space is vast, we imagine emptiness sprinkled with stars. Yet these images are not wrong because they lack detail. They are wrong because they compress reality into something the brain can tolerate. Scale is not just a matter of size, it is a matter of separation, of isolation of time stretched so far that motion itself becomes difficult to grasp. In the universe, distance is not a background feature. It is the dominant force shaping everything that exists. Most visualizations hide this truth. Planets are shown close together so they fit on a screen. Stars crowd together in glowing spirals. Galaxies appear as dense cities of light. These images are useful, but they quietly erase the most important fact of all. Almost everything in the universe is far apart. Not slightly far, not inconveniently far, but separated by distances so extreme that even light, the fastest thing we know, must travel for years, centuries or longer just to cross them. This is where understanding begins to break. The brain does not feel the difference between a million and a billion. It treats both as simply large. It cannot naturally grasp the idea that two objects can be part of the same structure, yet never meaningfully interact over the entire lifetime of the universe. It struggles to accept that most of what exists will never be reached, touched, or influenced, no matter how advanced a civilization becomes. And yet this is the true architecture of reality. The universe is not a crowded place. It is not packed with matter, life, or light. It is a vast framework where islands of substance float in oceans of near nothingness, connected only by gravity and time. The emptiness is not a gap between things. It is the main feature. To understand the true scale of the universe, we cannot leap directly to its largest limits. Doing so only replaces one abstraction with another. Instead, we must move carefully, step by step, outward from what feels familiar, from the ground beneath our feet, from the thin shell of air that keeps us alive, from the fragile world we call home. Only then does the real story of scale emerge, not as a list of distances, but as a gradual dismantling of intuition, a realization that the universe is not just large, but structured in a way that makes separation inevitable. And this journey does not begin among galaxies or cosmic horizons. It begins here, on a small world suspended in an ocean of space that is already far larger than it appears. At first glance, Earth feels immense. Continents stretch beyond the horizon. Oceans seem endless. The sky arches overhead like a vast dome. From the surface, it is easy to believe we live in a large world. But this sense of scale is an illusion created by proximity. Earth's diameter is a little over 12,000 kilometers. That number sounds impressive until distance stops being measured in kilometers and begins to be measured in emptiness. What truly defines Earth's place in the universe is not its size, but how thin and isolated its habitable layer really is. If Earth were reduced to a smooth sphere 1 meter across, the entire biosphere would vanish almost completely. The oceans would become a film thinner than a human hair. The atmosphere would shrink to a layer so delicate it could barely be seen. Everything that has ever lived would exist within a fragile skin clinging to the surface. From space, this fragility is already visible. Photographs taken from orbit reveal a razor-thin blue line wrapped around the planet. That line contains every breath ever taken, every cloud ever formed, every ecosystem that has ever existed. Beyond it, conditions change instantly. Temperature drops, radiation rises, life ends. Even the distances we consider vast on Earth collapse under cosmic perspective. Flying across an ocean takes hours. Circling the planet takes less than a day. Light itself can travel around Earth more than 7 times in a single second. This speed exposes a critical truth. Earth is not large in space. It is compact, tightly bound, and sharply defined. Gravity keeps everything close. The Moon, which feels distant to human travel, orbits at a range that still belongs firmly to Earth's immediate neighbourhood. If Earth were the size of a marble, the Moon would be a grain of sand just a few centimetres away. Beyond that, space opens rapidly. There is no gradual transition, no fading boundary where Earth slowly becomes part of something larger. Instead, there is a sudden drop into scale so wide that Earth becomes indistinguishable from a point. This is why Earth dominates our intuition. We evolved inside this narrow bubble of distances where everything feels connected. Weather systems interact. Seasons cycle. Life responds quickly to change. But this closeness is rare. Earth is not representative of the universe. It is an exception carved out by gravity, chemistry, and time. A small island where distances are short enough for complexity to emerge. Once we leave this island, the rules change immediately. To understand the true scale of the universe, we must first let go of the idea that Earth is a meaningful unit of measure. It is not a stepping stone to cosmic size. It is a microscopic refuge surrounded by space that expands far faster than intuition can follow. And just beyond this refuge lies a structure that already begins to challenge the limits of human imagination. The solar system. The solar system is often imagined as a compact family of worlds, a bright star at the center surrounded by planets moving in graceful, tightly packed orbits. This image appears everywhere, from textbooks to films, because it fits comfortably inside the human mind. Reality does not. If the Sun were scaled down to the size of a large beach ball, Earth would be a grain of sand orbiting more than 20 meters away. Jupiter, the largest planet in the system, would still be only a small marble, placed hundreds of meters from the Sun. Between these points, there would be nothing to see. Not darkness filled with stars, not clouds of matter, just space. The distances between planets are so large that the planets themselves almost disappear from relevance. Their orbits are not pathways carved into a crowded medium. They are lonely loops traced through emptiness. Light makes this clear in a way numbers cannot. Sunlight reaches Earth in about 8 minutes. It takes more than 4 hours to reach Neptune. This is the same light travelling uninterrupted because there is almost nothing to slow it down. Even this familiar system does not end where most diagrams stop. Beyond Neptune lies a vast region of scattered ice and rock, followed by a realm so distant that its objects have never been seen directly. This outer domain, known as the Oort cloud, is not a ring or a shell in the ordinary sense. It is a loose spherical halo of debris extending far beyond the planetary orbits. Its inner edge begins thousands of times farther from the Sun than Earth is. Its outer boundary may stretch nearly a quarter of the way to the nearest star. At this scale, the Sun's influence becomes faint. Its gravity weakens, orbits slow to a crawl. A single revolution can take millions of years, and still space dominates. Even within the solar system, matter is the exception. The combined volume of every planet, moon, and asteroid is negligible compared to the void that surrounds them. The system is not defined by its objects, but by the distances between them. This emptiness has consequences. Travel becomes a question of endurance rather than direction. Signals fade, energy spreads thin. Time itself becomes a primary cost of movement. Spacecraft leaving Earth do not pass through layers of structure. They enter a widening desert where each additional unit of distance yields less to see and more to cross. The solar system already shows the pattern that will repeat at every larger scale. Structure surrounded by overwhelming absence, islands of matter separated by gulfs of nothing, and yet this vast domain, stretching billions of kilometers in every direction, is still only a small pocket within a much larger emptiness. Because beyond the furthest reach of the Sun's influence, another scale of separation begins. The distance between stars. For most of human history, the solar system felt complete at the orbit of the outer planets. Even today, many diagrams quietly suggest that once Neptune is past, space simply continues on toward the stars. In reality, the Sun's domain extends far beyond the planets, fading slowly into the surrounding galaxy. This extended boundary is not marked by a wall or a sharp edge. It is defined by gravity becoming weak enough to surrender its hold. Far past the orbit of Neptune, past the scattered disk of icy remnants, lies a distant reservoir of ancient debris. This region, known as the Oort cloud, is not a band or a disk, but a vast diffuse sphere surrounding the Sun. Its inner regions begin tens of thousands of astronomical units from the centre. Its outer edge may stretch almost a light year away. At these distances, the solar system loses its familiar shape. The Sun is no longer a blazing centre, but a bright point among many others. Orbits become so slow that motion is measured in geological timescales rather than years. Objects in the Oort cloud drift in darkness so complete that even reflected sunlight is nearly non-existent. A single revolution around the Sun can take millions of years. Some objects may never complete a full orbit before being nudged away by passing stars or the gentle pull of the galaxy itself. This is the true edge of home. Beyond this boundary, the Sun can no longer reliably claim what lies nearby. Gravitational ownership becomes shared, uncertain, temporary. The solar system dissolves into the larger structure of the Milky Way. Spacecraft reveal how quickly this transition occurs. Voyager, one travelling faster than any human-made object, took decades just to reach the outer regions where the solar wind fades into interstellar space. Even now it remains deep inside the Sun's gravitational influence. Reaching the inner edge of the Oort cloud would take thousands of years. Crossing it could take tens of thousands more. And yet in cosmic terms, this entire realm is still a narrow bubble. The distance from the Sun to the outer edge of the Oort cloud is immense by planetary standards. But compared to the separation between stars, it is small. Two neighbouring stellar systems can pass close enough to disturb each other's Oort clouds without their planets ever interacting. This overlap reveals a subtle truth. Solar systems are not isolated bubbles floating in perfect solitude. Their outermost boundaries blur into one another. Gravity reaches outward, touches and withdraws over millions of years. What we call interstellar space does not begin suddenly. It emerges gradually as the Sun's influence thins and the galaxy's influence takes over. And once this threshold is crossed, scale changes again, because the distances that follow are no longer measured in millions or billions of kilometers. They are measured in light years. And this is where separation becomes absolute. The space between stars. When the Sun finally loses its grip, space does not reveal a new structure waiting nearby. It reveals almost nothing at all. The nearest star system, Alpha Centauri, is often described as close. In cosmic language, it is a neighbour. In human terms, it is unreachable. Light moving at the maximum speed allowed by the universe takes more than 4 years to cross this gap. Not 4 years of drifting slowly through darkness, but 4 years of relentless motion without pause, without resistance. Anything slower must measure the journey in tens of thousands of years. This distance defines the true nature of interstellar space. Stars are not arranged like lamps in a room. They are not evenly spaced points filling a volume. They are isolated sources of light separated by enormous regions where almost nothing exists. If the Sun were reduced to the size of a grain of sand, the nearest star would be another grain placed several kilometers away. Between them there would be no planets, no clouds, no landmarks, just empty distance. This emptiness is not merely visual, it is physical. Interstellar space contains a few atoms per cubic centimetre. Not molecules, not dust grains. Individual atoms drifting alone, separated by distances larger than entire cities. Even these atoms rarely interact. As a result, stars evolve in near isolation. They are born, burn and die without ever touching one another. Supernova can flood space with radiation, but even these explosions dissipate long before crossing the gaps between most stellar systems. Gravity is the only long-range connection, and even it weakens rapidly with distance. The galaxy is not a dense swarm of stars influencing one another directly. It is a collection of solitary systems bound together statistically rather than physically. Each star follows its own orbit around the galactic center, largely unaware of its neighbors. This separation has profound consequences. Travel between stars is not a problem of navigation, it is a problem of scale. Energy must be carried across distances so vast that even sustaining motion becomes difficult. Communication suffers the same fate. A message sent today arrives years later unchanged by anything it passed through, because there was nothing there to interact with it. From within a planetary system, stars appear numerous. From within a galaxy, they appear sparse. Perspectives shift with scale, and each shift reveals greater isolation than the last. Yet even this vast emptiness is not the dominant scale. Stars isolated as they are still belong to a larger structure. They orbit together, forming a disk hundreds of thousands of light years across. They trace spiral arms, move through stellar streams, and respond to a shared gravitational center. The Milky Way is not a collection of stars placed randomly in space. It is a structure shaped over billions of years, defined as much by the voids between stars as by the stars themselves. To understand the true scale of the universe, the next step is unavoidable. We must stop thinking in terms of stars as destinations. We must begin thinking of them as particles inside something far larger. A galaxy. From the outside, a galaxy looks dense. Spiral arms glow, cores burn brightly, billions of stars appear packed together in sweeping arcs of light. This image is one of the most persistent illusions in astronomy. Inside a galaxy, space is still overwhelmingly empty. The Milky Way spans roughly 100,000 light-years from edge to edge. Within that enormous disk reside hundreds of billions of stars. At first glance, that number suggests crowding. In reality, it describes separation. Even near the galactic center, where stars are most concentrated, the average distance between them remains measured in light years. In the outer regions, that separation grows even larger. The spiral arms are not solid structures. They are regions of slightly higher density drifting through a sea of space. If the Milky Way were reduced to the size of a continent, every star would shrink to something smaller than a grain of dust. Each grain would be separated from the next by kilometers of empty terrain. The glowing bands seen in images would vanish entirely. This emptiness is why galaxies can pass through one another. When the Milky Way and Andromeda begin their slow merger, billions of years from now, stars will rarely collide. Entire solar systems will pass between one another untouched. The galaxies will blend not by impact, but by gravity reshaping their shared orbits. Light again reveals the scale more clearly than size alone. A beam of light takes 100,000 years to cross the Milky Way. During that time, civilizations can rise and vanish. Species can emerge, evolve and disappear. The galaxy does not respond quickly. Its motions are slow, deliberate, almost frozen on human timescales. From within this structure, perspective becomes deceptive. Looking up from Earth, the night sky feels crowded. Thousands of stars fill the darkness. But this is a projection effect. We are seeing along the thin plane of the galactic disk, peering through enormous distances where stars align by chance. If the galaxy were viewed edge-on from within, most directions would reveal almost nothing at all. Our own position highlights this truth. The Sun orbits far from the galactic center in a region where stellar density is low. Its nearest neighbors are light-years away. Its path around the galaxy takes more than 200 million years to complete a single loop. This motion binds the stars together without forcing them close. A galaxy is not a solid object. It is a dynamic system where gravity provides coherence, not contact. Stars move independently, bound only by the collective mass of everything else. And yet, despite its enormous scale, a galaxy is still a finite island. Beyond its faint outer halo, starlight thins rapidly. Gas becomes rare. Gravity loosens its grip. The structure fades into darkness. What lies beyond is not another dense layer of stars waiting nearby. It is a gulf measured in millions of light years. The true test of scale does not come from understanding a galaxy's size. It comes from realizing how alone each galaxy truly is. To grasp that isolation, we must step outside the Milky Way entirely, into the space between galaxies. Leaving a galaxy does not feel like crossing a border. There is no final star, no clear boundary where structure suddenly ends. Instead, starlight thins, gradually fading into a darkness that grows deeper with every passing light year. Between galaxies, space expands into its dominant form. The distance from the Milky Way to Andromeda is often cited as a simple number, a few million light years. On paper it sounds manageable. In reality, it represents a gulf so vast that even entire galaxies appear as isolated points drifting in an ocean of nothing. If the Milky Way were reduced to the size of a city, Andromeda would be another city hundreds of kilometers away. Between them, there would be no towns, no roads, no scattered lights, just open terrain stretching beyond sight. This region is not empty in an absolute sense, but it is close. A few stray atoms drift through intergalactic space. Occasional photons pass through carrying ancient information from distant sources. But matter structure and activity become exceedingly rare. Galaxies themselves reveal this isolation. Each one is surrounded by a vast halo of dark matter extending far beyond its visible stars. These halos define how galaxies move and interact long before they ever come close. Long before starlight overlaps, gravity is already shaping their slow dance. The local group, which includes the Milky Way and Andromeda, contains dozens of galaxies. Yet even within this small collection, separation dominates. Dwarf galaxies orbit in wide elongated paths. Interactions unfold over billions of years. Collisions are not sudden events. They are prolonged processes where gravity stretches and distorts structures long before contact ever occurs. Most of the time, galaxies simply drift. From this perspective, galaxies resemble islands more than cities. Each one carries its own history, its own population of stars, its own internal dynamics. The space between them is not a corridor of travel, but a barrier of scale. Light again defines the reality. When we observe distant galaxies, we are not seeing them as they are now. We are seeing ancient light that has crossed intergalactic space for millions or billions of years. The voids between galaxies act as time machines stretching the present into the deep past. As distance increases, isolation intensifies. Clusters of galaxies form where gravity has had enough time to draw matter together, but even these clusters occupy a small fraction of the universe's volume. Most space lies far from any cluster, far from any galaxy, far from any source of light. The universe does not distribute its contents evenly. It concentrates matter into nodes and leaves the rest almost untouched. This realization changes how scale must be understood. It is not enough to count stars or galaxies. One must account for the vast regions where nothing happens at all, where time passes without events, where light crosses distances that dwarf everything inside galaxies themselves. And even these immense dark spaces are not the largest structures in existence. They are only the gaps between patterns that emerge on still greater scales. To see those patterns, we must pull back further, beyond individual galaxies, beyond small groups, into the architecture that binds entire regions of the universe together. When distance increases far enough, isolation begins to reveal structure. Galaxies are not scattered randomly through space. Their positions follow patterns shaped by gravity acting over billions of years. On the largest scales, the universe resembles neither a uniform fog nor a simple collection of islands. It forms a vast interconnected framework. This framework is known as the cosmic web. Galaxy clusters emerge at the web's densest intersections. Each cluster contains hundreds or even thousands of galaxies bound together by gravity. These are the largest structures in the universe that are still held together as single systems. Inside a cluster, galaxies move at tremendous speeds. They orbit a shared center of mass dominated not by stars or gas but by dark matter. Hot plasma fills the space between galaxies, glowing faintly in X-rays, tracing the gravitational wells that hold everything together. Yet even here, space remains dominant. Galaxies inside clusters rarely collide directly. They pass by one another at distances measured in tens of thousands of light years. Interactions unfold slowly through tidal distortions and long gravitational encounters rather than sudden impacts. Clusters themselves are not evenly distributed. They line up along elongated filaments that stretch across hundreds of millions of light years. These filaments form the skeleton of the cosmic web, threading through space like faint bridges of matter. Along them, galaxies drift, emerge, and accumulate over cosmic time. Between these filaments lie enormous regions where matter is scarce. The web does not fill space, it outlines it. On even larger scales, clusters group into superclusters. These are not tightly bound objects, but extended regions where gravity subtly influences motion across vast distances. Our own galaxy belongs to such a structure, part of a supercluster, defined not by sharp edges, but by shared gravitational flow. These flows reveal something crucial. Galaxies are not simply expanding away from one another as space grows. They also stream along invisible gradients shaped by mass distributions too diffuse to see directly. Motion in the universe is guided as much by absence as by presence. The cosmic web did not form instantly. It emerged from tiny fluctuations in the early universe, amplified over billions of years by gravity. Regions that were slightly denser attracted more matter. Regions that were slightly emptier lost it. Over time, contrast increased, carving space into filaments, nodes, and voids. What makes this structure difficult to grasp is its scale. Filaments are not roads or bridges in any practical sense. They are vast corridors of slightly higher density, where the distance between galaxies is still measured in millions of light years. Superclusters are not solid assemblies, but patterns frozen into the expansion of space itself. From far enough away, even these structures begin to fade. The cosmic web does not fill the universe uniformly. It occupies only a fraction of cosmic volume. Most space lies far from any filament, far from any cluster, far from any galaxy. This realization forces a shift in perspective. The largest known structures are not defined by what they contain, but by how little they occupy. Matter traces delicate lines through an otherwise empty expanse. Structure is the exception, not the rule, and this raises an unsettling question. If clusters and filaments define the universe's architecture, what defines everything else? The answer lies in the regions they surround. Vast domains where the web thins almost to nothing, where galaxies are rare, where distance reaches its purest form. To understand the true scale of the universe, we must now turn toward what dominates it by volume. The cosmic voids. On the larger scales, the universe is not defined by what it contains. It is defined by what it lacks. Between the filaments and clusters of the cosmic web lie regions so vast and so empty that they dominate the universe by volume. These regions are known as cosmic voids. A void is not a simple gap. It is a structured absence. Typical voids span tens of millions of light years. Some stretch across hundreds of millions. Within them, galaxies are rare, often isolated, sometimes absent altogether. The density of matter drops to a fraction of the cosmic average. If the cosmic web were drawn in ink, voids would be the paper. This imbalance is not subtle. More than 3/4 of the observable universe's volume lies inside these regions. Most of space exists far from stars, far from galaxies, far from any source of sustained light. From inside a void, the universe would look profoundly different. The night sky would contain fewer galaxies. The nearest cluster might lie tens of millions of light years away. Large-scale structure would not surround the observer. It would recede. Void galaxies, when they exist, evolve differently. They experience fewer interactions. Their histories unfold in relative isolation. Even gravity behaves more gently, stretched thin across enormous distances. These regions did not form by accident. In the early universe, matter was distributed almost evenly, with only tiny fluctuations in density. As expansion continued, gravity amplified those differences. matter flowed towards slightly denser regions, leaving behind expanding zones of depletion. Voids are not static holes. They grow. As matter drains outward, voids expand faster than the average universe. Their interiors become emptier with time. Boundaries sharpen, filaments thin, contrast increases. This growth reshapes everything around them. Clusters are pushed apart, filaments stretch. The cosmic web becomes more pronounced not because matter increases, but because emptiness does. In this sense, voids are active participants in cosmic evolution. They influence motion expansion and structure simply by being empty. Understanding this reverses a common assumption. The universe is not a stage filled with objects. Objects are rare interruptions in a vast continuum of near-nothingness. What we call structure exists because most space allows it to stand out. Scale becomes clearer here. Distances inside voids are not punctuated by landmarks. There is no gradual sequence of stars or galaxies to mark progress. Movement across these regions is defined almost entirely by time. Light entering a large void travels for millions of years without encountering anything substantial. No dust clouds, no stars, no gravitational well strong enough to bend its path significantly. From the perspective of scale, voids are pure distance. They represent the universe at its most honest, not dramatic, not luminous, but vast beyond intuition. And yet even these enormous regions are not the final measure. Voids, filaments, clusters, and galaxies together form a pattern that still fits within a larger boundary. A limit imposed not by space itself, but by time and light. To reach the true edge of what we can comprehend, we must confront that boundary. The observable universe. There is a boundary to what we can see, not because the universe ends there, but because light does. The observable universe is not defined by distance alone. It is defined by time. Light travels at a finite speed. Because the universe has a finite age, there is a maximum distance from which light has had enough time to reach us. That distance marks the horizon of observation. At first glance, this seems straightforward. If the universe is about 13.8 billion years old, then we might expect the observable universe to have a radius of 13.8 billion light years. It does not. Space itself has been expanding while light was in transit. As photons cross the cosmos, the distances between their points of origin and their destination continue to stretch. As a result, the galaxies whose light we see today are now far farther away than their light travel time suggests. The observable universe extends roughly 46 billion light-years in every direction. This number does not represent how far light has travelled. It represents how far its sources now reside. This distinction matters. When we observe a distant galaxy, we're not seeing where it is. We are seeing where it was. The image arrives frozen in time, carrying information from an era when the universe was younger, denser, and hotter. At great distances, this effect becomes extreme. Some of the light reaching us today was emitted when galaxies were only beginning to form. Others come from a time before galaxies existed at all, when matter was still distributed as glowing plasma. Beyond that lies the cosmic microwave background, the oldest light we can detect released when the universe first became transparent. This radiation does not mark the beginning of everything. It marks the limit of visibility. Before that moment, the universe was opaque. Photons could not travel freely. No signal from earlier times can reach us directly. The observable universe is therefore not a complete map of reality. It is a shell defined by what light has been able to deliver. Inside this shell lies everything we can ever measure with telescopes. All galaxies, all clusters, all voids we can observe exist within this finite volume. Outside, it may lie more of the same or something profoundly different. We do not know. What we do know is that the observable universe is not static. As time passes, the horizon changes. New regions come into view. Others slip away, carried beyond reach by accelerating expansion. Some galaxies we see today will eventually fade from observation, their light stretched beyond detectability. This introduces a quiet asymmetry. There are objects we can see but can never reach. Their light arrives, but no signal we send will ever arrive in return. Causality itself becomes directional. Distance here is no longer just separation. It is disconnection. Two galaxies can exist within the same universe governed by the same physical laws yet forever isolated from one another's future. Their histories may overlap. Their destinies will not. The observable universe then is not a container holding everything that exists. It is a moving boundary shaped by expansion time and the speed of light, a horizon that reveals reality while simultaneously hiding most of it. Understanding this shifts the meaning of scale once again. The larger structures we can map fit comfortably inside this horizon, but the universe itself may extend far beyond it, repeating patterns or introducing scales we cannot imagine. To speak of the true scale of the universe, we must now confront this final question. What lies beyond what we can see? The observable universe feels complete only because it is all we can access. But completeness is an illusion created by limitation. The boundary defined by light is not a physical wall. It does not mark an edge where space ends or reality changes form. It simply marks the furthest distance from which information has had time to arrive. Beyond this horizon, the universe continues. How far it extends is unknown. It may stretch far beyond the observable region, repeating the same large-scale structures again and again. Or it may differ in ways we cannot test, governed by conditions that lie permanently outside our reach. What matters is not the specific possibilities, but the implication. Everything we have measured, every galaxy counted, every structure mapped represents only a fraction of what exists. The observable universe is a sample, not a total. Cosmological models suggest that the universe may be vastly larger than the region we can see. Some estimates place its total extent at hundreds or thousands of times greater. Others allow for scales so large that meaningful comparison becomes impossible. At such extremes, scale loses its connection to intuition entirely. Distance no longer serves as a path between points. It becomes a statement about causality, about which events can ever influence one another. Regions beyond the observable horizon are not merely far away, they are causally disconnected. No signal, no matter how fast or energetic, can cross the expanding space that separates them from us. This disconnection reshapes the concept of existence. Something can exist, follow the same physical laws, and still be forever irrelevant to everything we will ever observe. Its history unfolds independently. Its future never intersects with ours. From a human perspective, this is unsettling. We instinctively tie existence to influence. To be real is to matter, to interact, to be capable of connection. The universe challenges this assumption. Most of what exists may never affect us in any way, not because it is hidden, but because distance itself prevents interaction. This is the final consequence of scale. The universe is not simply large. It is structured so that isolation increases with size. Connections weaken, shared futures dissolve, and yet within this immense fragmented reality awareness arises, on a small planet, round an ordinary star, inside a galaxy that drifts through one filament of a vast cosmic web. The true scale of the universe does not diminish that awareness. It contextualizes it. Understanding scale does not make existence smaller. It makes it rarer. Everything we know, everything we will ever know, occupies a tiny region of a reality that extends far beyond sight. A reality where distance is not just separation, but a fundamental property of how the universe unfolds. This is the true scale of the universe. Not a number, not a map, but a structure in which most things will never meet. And within that structure, a quiet realization remains. To understand how far the universe extends is to understand how alone each point within it truly is. When the journey through scale ends, nothing dramatic happens. There is no final boundary crossed, no sudden revelation waiting at the edge, only silence. The universe does not announce its size, it does not frame itself for understanding. It simply exists arranged in layers of distance so vast that meaning must be constructed slowly piece by piece. What makes scale difficult is not the mathematics, It is the emotional gap between what can be known and what can be felt. Numbers describe distances. Experience does not. Throughout this journey, one pattern has repeated without exception. As scale increases, connection weakens. Structures become rarer. Interaction slows. Isolation grows. From planets to stars. From stars to galaxies. From galaxies to the observable horizon, at every step emptiness dominates. This is not a flaw in the universe's design. It is the design. Distance regulates interaction. It preserves structure by preventing collapse. It allows complexity to exist locally while remaining rare globally. In a universe without distance, everything would merge into uniformity. In a universe defined by distance, diversity survives. This reframes humanity's place. We are not insignificant because the universe is large. We are significant because awareness appears at all within such separation. Because consciousness arises in regions where distance briefly relaxes its grip. A planet where molecules interact often enough to build memory. A star stable enough to provide time. A galaxy quiet enough to avoid constant disruption. These are not guaranteed outcomes. They are narrow windows carved into scale. The true scale of the universe does not ask us to feel small. It asks us to feel precise, to recognize that existence is not spread evenly, that meaning is local, that connection is rare. Everything we have ever observed exists inside a thin shell of visibility floating within, a reality that may be vastly larger and forever unreachable. Yet within that shell, the universe has learned to look back at itself. That may be the most remarkable fact of all. In the next journey, scale will take a different form. Not distance, but time. Not separation, but delay. Because even when space can be crossed, time often cannot. And sometimes the longest distances in the universe are not measured in light years. They are measured in light years ago. Distance was only the first barrier. Throughout this journey, scale revealed itself as separation. Objects grew farther apart. Interaction weakened. Connection became rare, but there is another dimension where scale exerts even greater control. Time. Light does not merely travel across space. It travels across history. Every distant object we observe is already gone, replaced by a present we can never see directly. In the largest structures of the universe, distance and time become inseparable. To look farther is to look deeper into the past. To understand scale is to realize that the universe is not experienced simultaneously. Some events unfold so slowly that motion disappears. Others occur so long ago that their consequences arrive after civilizations have vanished. Causality stretches, thins, and eventually breaks. The universe is not only large, it is delayed. This raises a new question, one that distance alone cannot answer. If space isolates objects, time isolates eras. If galaxies drift apart forever, moments do the same. The next journey does not move outward, it moves backward, into the time it takes for light to cross the universe, into distances measured not by how far but by how long ago. Because beyond a certain scale, the universe stops being a place. It becomes a history, and that history is still arriving. In everyday life, distance and time are separate ideas. You travel somewhere and time passes as a consequence. In the universe, the two are inseparable. A light year is not just a measure of how far something is, it is a measure of how long ago it was. Every photon carries a timestamp. When it reaches us, it tells a story about the universe at the moment it was released, not the moment it is received. Looking outward is never an act of observation alone. It is an act of archaeology. Nearby stars appear almost current. Their light left only a few years ago, but as distance increases, the present recedes rapidly. The light from the center of the Milky Way began its journey tens of thousands of years before human civilization emerged. The glow of nearby galaxies left when early humans were learning to shape stone tools. Farther still, the light from massive clusters began traveling before Earth had complex life at all. At extreme distances, this separation becomes absolute. Some galaxies we observe today no longer exist in the form we see. They have merged, transformed, or faded into darkness. What arrives at our telescopes is not a snapshot of reality, but a preserved moment that can never be revisited. This creates a layered universe. Space is not filled with objects as they are now. It is filled with records of what they once were, stacked by distance, arranged by time. The farther we look, the older the universe becomes. This layering explains a subtle but critical truth. There is no single cosmic present. Different regions of the universe exist in different eras relative to us. Two galaxies separated by billions of light-years do not share the same now. They occupy different slices of cosmic history connected only by the arrival of light. Scale amplifies this effect. On small scales, delay is negligible. On planetary scales, it becomes noticeable. On galactic and intergalactic scales, it dominates. By the time we reach the observable horizon, the universe we see is almost entirely a memory. This has consequences for understanding structure. The cosmic web we map is not frozen. It is a composite image assembled from different epochs. Filaments we observe at great distances were younger, denser, and less evolved than nearby ones when their light was emitted. The universe we reconstruct is therefore not a single state. It is a time-averaged portrait spanning billions of years. Even the oldest light we can detect carries this imprint. The cosmic microwave background does not show the universe as it is. It shows the universe as it was when matter and radiation first separated us. That image has been travelling for nearly the entire age of the cosmos, crossing expanding space to reach us. From this perspective, scale reaches its final form. Distance becomes delay. Delay becomes disconnection. And disconnection becomes a limit on what can be known. There are events whose light has not arrived yet. There are regions whose future will never intersect with ours. And there are moments that existed but left no signal we can ever detect. Understanding the true scale of the universe means accepting this constraint. We do not observe reality directly. We observe its echoes. And the farther those echoes travel, the more the universe reveals not its size but its age. Beyond a certain distance, the question is no longer where something is, it is when it was. When distance becomes time and time becomes delay, a deeper boundary appears. Not a limit of vision, but a limit of influence. This boundary is known as the causal horizon. In an expanding universe, space itself grows between objects. If that expansion is slow, signals can eventually cross the gap. If it is fast enough, separation becomes permanent. Some regions of the universe are already beyond causal contact with us, not because they are hidden, but because the space between us and them expands faster than light can traverse. No message sent today will ever arrive there. No response sent back will ever reach us. These regions are not hypothetical. They exist right now. Galaxies near the edge of the observable universe are visible only because their light began its journey long ago. Since then, expansion has carried them away so rapidly that they are no longer reachable even in principle. They are part of our visible past but not our shared future. This creates a subtle division. The observable universe is not the same as the causally connected universe. We can see farther than we can ever influence. Vision extends beyond reach. As time continues, this divide grows. Dark energy accelerates expansion, pushing distant regions away more quickly. Over billions of years, fewer galaxies will remain visible. Clusters outside our local region will fade as their light stretches beyond detection. Eventually, the night sky itself will change. Far in the future, observers within the Milky Way's merged remnant may see only their own galaxy. The cosmic web will vanish from view. The observable universe will appear smaller not because it is shrinking, but because access is closing. Scale in this sense is not fixed, it evolves. The universe does not simply grow larger, it grows quieter. Connections that once existed dissolve as expansion stretches space beyond interaction. This reshapes the meaning of cosmic structure. Superclusters are not permanent assemblies. Filaments do not bind the universe forever. On the longest timescales, gravity loses its contest with expansion. What remains are isolated islands of matter drifting apart into darkness. From within such an island, the universe will appear finite and self-contained. Future observers may infer a much smaller cosmos, unaware of the vast structures that once lay beyond sight. Scale then is not only about size, it is about access. What exists is larger than what can be seen. What can be seen is larger than what can be reached. And what can be reached is smaller still. This hierarchy defines reality more powerfully than distance alone. Two civilizations could arise in regions governed by identical physical laws formed from the same early universe, yet remain forever unable to exchange a single particle or signal. Their histories unfold in parallel, never intersecting. This is not separation by choice or technology. It is separation enforced by the geometry of space and time. Understanding this completes the journey through scale. The universe is vast, not merely because it contains great distances, but because it fragments existence into disconnected futures. It allows complexity to arise locally while preventing it from spreading universally. Scale ensures isolation. Isolation preserves diversity. And diversity gives rise to meaning in small pockets of an otherwise indifferent expanse. The true scale of the universe is therefore not just a measure of how much exists, it is a measure of how little can ever be shared. When scale fragments the universe into isolated regions, a paradox emerges. The larger the universe becomes, the more meaning retreats inward. At small scales, interaction is frequent. Particles collide, chemistry unfolds, information moves quickly enough to matter. At larger scales, interaction thins. Signals weaken, causality stretches, shared outcomes become rare. This is not an accident of physics. It is a consequence of scale itself. Distance filters influence. Time delays consequence. Expansion separates futures. Together they create a universe where significance is not global but local. Galaxies do not shape the fate of the entire cosmos. Stars do not coordinate their evolution. Civilizations, if they arise elsewhere, do so in near total independence. The universe does not converge toward a single outcome. It diverges. This divergence explains why complexity can exist at all. If everything were close, constant interaction would erase structure. If everything were connected, differences would smooth out. Uniformity would dominate. Instead, scale creates compartments. Within these compartments, matter has time to organize. Energy can flow in stable patterns. Memory can accumulate. Life can persist long enough to notice its surroundings. A planet becomes meaningful not because it is central, but because it is protected by distance. A galaxy becomes stable not because it is isolated, but because it is isolated enough. Even the observable universe itself is a compartment, a region where shared history is possible, where light has had time to arrive, where cause and effect can still meet. Beyond it, reality may continue endlessly, but meaning as we experience it does not. This reframes the question of scale. The universe is not asking to be fully understood. It is structured so that understanding is necessarily partial. Every observer occupies a limited vantage point bounded by horizons of space and time. What we call the universe is in practice the region that can influence us and be influenced in return. Everything else exists without reference to our story. This does not diminish discovery. It sharpens it. Knowing that knowledge is local gives weight to observation. It makes each measurement a rare connection across distance and time. Each photon received is a successful crossing of barriers that most information never overcomes. Scale then is not a cold abstraction. It is the condition that makes moments possible. Within a vast divided reality, islands of coherence form. On those islands, matter remembers. On some of them, awareness arises. The universe does not center on these islands, but it allows them, and that allowance is written directly into its scale. To understand the true scale of the universe is not to feel overwhelmed by size. It is to recognize the narrow windows where connection survives, where time aligns closely enough with space for meaning to emerge. Everything else is distance. At the end of this journey, scale no longer feels like a number. It feels like a condition. The universe is not vast in the way an empty field is vast. It is vast in the way separation accumulates, in the way interaction thins, in the way connection becomes increasingly difficult then impossible, from planets to stars, from stars to galaxies, from galaxies to horizons. Each step outward did not merely increase distance, it reduced shared reality. What we call the universe is therefore not a single unified arena. It is a mosaic of regions, each governed by the same laws yet unfolding independently. Most of these regions will never exchange matter, energy, or information, and yet within this fragmentation something remarkable occurs. On a small world orbiting an ordinary star inside a quiet corner of a galaxy, matter has learned to organize itself, to store information, to become aware of distance, time, and limitation. This awareness exists only because scale permits it. If the universe were smaller, constant interaction would erase stability. If it were denser, complexity would collapse under its own interference. If it were more connected, diversity would vanish. Scale protects difference by enforcing distance. The same structure that isolates galaxies allows atoms to form molecules. The same separation that divides cosmic futures allows memories to persist locally. The same emptiness that dominates the universe by volume gives structure room to exist at all. In this sense, scale is not hostile to meaning. It is the reason meaning survives. The true scale of the universe does not reduce our place within it. It defines it. We are not central. We are not unique by position, but we are rare by circumstance. A brief alignment of space-time and stability, a moment where distance is small enough and time slow enough for awareness to arise. Everything we have ever known exists inside this narrow window. Everything we will ever know will remain confined to it. Beyond lies more universe, more distance, more futures that never intersect with ours. But scale does not ask us to reach them. It asks us to understand the one region where connection is still possible. Here, now. On a small island of coherence suspended inside a reality too large to ever be fully shared. That is the true scale of the universe. The universe reveals itself generously. Every direction we look, light arrives from unimaginable distances. Galaxies spill across the sky. Structures stretch farther than intuition can follow. At first glance, it feels as if the universe is open to us, laid out in full view. But visibility is not access. Seeing something in the universe does not mean it can be reached. It does not mean it can be influenced. And it does not mean it can ever respond. This distinction is easy to miss. On Earth, sight and reach are closely linked. If you can see a mountain, you can walk toward it. If you see a light in the distance, you can approach it given enough time. Distance delays contact, but it rarely forbids it. The universe does not work this way. Beyond a certain scale, distance becomes a permanent barrier, not because it is large, but because it is paired with time expansion and limits built into reality itself. Much of what we observe exists in a strange state. Its light reaches us, its present does not. Some galaxies we see are already moving away faster than any signal could ever follow. Their images arrive faithfully while their futures recede forever beyond reach. They are visible but inaccessible, present in our sky but absent from our causal world. This creates a quiet contradiction at the heart of cosmology. We live in a universe that allows observation far beyond interaction, a universe that shows us far more than it ever allows us to touch. The farther we look, the more extreme this imbalance becomes. At interstellar distances, travel becomes impractical. At intergalactic distances, it becomes meaningless. At cosmic scales, even communication collapses under delay and expansion. Light alone survives the journey, and even light arrives late. This is why the universe feels strangely silent. Not because nothing exists, not because life is rare, but because the structure of space and time prevents most things from ever meeting. Two civilizations could arise in distant galaxies governed by identical laws shaped by similar histories and still remain permanently unaware of one another. Their signals cross the universe too slowly. Their timelines fail to overlap. Their futures diverge before contact is possible. Silence in this context is not evidence of emptiness. It is evidence of separation, To understand why the universe is so difficult to reach across, we must move beyond size alone. We must examine the limits that distance imposes on motion, communication, and shared history. This journey does not ask how large the universe is. It asks a more unsettling question. In a universe this vast, what can ever truly touch anything else? And how much of reality is destined to remain forever out of reach? When people imagine the challenge of reaching the stars, they usually picture distance as the enemy. The numbers seem overwhelming. Light years stretch beyond comprehension. The problem appears simple even if unsolvable. Things are too far away, but distance alone is not what makes the universe unreachable. If space was static, even extreme separation could in principle be crossed. Slowly, at great cost, over long spans of time, but crossed nonetheless. The deeper obstacle is not how far things are, it is how distance behaves. On Earth, distance is passive. A road does not grow longer while you walk it. A destination does not move away faster because you are approaching it. Time is the only price you pay. In the universe, distance is active. Space expands. Targets recede. The path itself changes while you travel. This transforms motion from a question of endurance into a question of possibility. Consider interstellar travel. Reaching a nearby star requires carrying energy across years of emptiness. Every kilogram of mass becomes a burden. Every system must survive isolation, radiation, and failure without external support. Even optimistic designs push against limits of fuel shielding and time, yet even these challenges are secondary. The real problem emerges when distance grows large enough that speed stops helping. No matter how fast a spacecraft travels, it cannot outrun the expansion of space on cosmic scales. No matter how efficiently it carries energy, time continues to separate origin from destination. Beyond a certain point, motion becomes symbolic rather than effective. This is why the idea of going somewhere breaks down. Interplanetary travel fits within a shared system. Interstellar travel stretches that system but remains marginally conceivable. Intergalactic travel leaves it entirely. Between galaxies, distances are not only vast, they are unsupported. There are no intermediate structures to slow time or resupply motion, no gravitational corridors that shorten the journey, only expanding space and diminishing influence. Even communication suffers the same fate. A signal sent across intergalactic distances arrives long after its context has vanished. Questions arrive after answers are no longer relevant. Information becomes disconnected from intention. At this scale, the universe stops behaving like a place and starts behaving like a process. Movement is not just slow, it is outpaced. This is why technological optimism fails to resolve the problem. Faster engines do not defeat expansion. Better fuel does not compress time. Advanced materials do not restore shared futures. The universe enforces separation not through hostility but through geometry. Distance stretches, time delays, and beyond a threshold connection dissolves entirely. This reframes how reach must be understood. Reaching something is not about pointing toward it and moving forward. It is about remaining within a region where cause and effect can still meet. Once that region is left behind, distance ceases to be a challenge to overcome. It becomes a boundary that cannot be crossed at all. This is the first reason the universe is mostly out of reach. Not because it is large, but because size, time, and expansion combine to turn separation into permanence. And even this is only the beginning, because the one thing that does cross the universe with ease is not matter, it is light. And light reveals a far deeper imbalance between what can be seen and what can ever be touched. Light is the universe's great exception. It moves without rest. It requires no fuel. It crosses distances that defeat every other form of motion. Where matter fails, light succeeds. This is why the universe appears so accessible. Telescopes gather photons that have traveled for millions or billions of years. They deliver images of galaxies, clusters, and cosmic structure with extraordinary fidelity. From a small planet, we reconstruct a map of the cosmos that spans almost its entire visible extent. But light does not bring access. It brings information without interaction. A photon arriving from a distant galaxy carries data about its origin. Its wavelength encodes motion, composition, temperature, and age. Yet the arrival of that photon does not affect the source in any way. The exchange is one-sided. We can observe distant objects. We cannot participate in their present. This difference is subtle at small scales. It becomes decisive at large ones. When we look at nearby stars, delay is minimal. The star we see still exists in roughly the same state. Signals sent today could in principle arrive while the system remains recognizable. At greater distances, this symmetry collapses. The light from many galaxies began its journey before Earth formed. By the time it arrives, those galaxies have changed profoundly. Some have merged, others have been torn apart. Many have faded beyond recognition. Yet their images persist. This creates a universe filled with ghosts. Not illusions, but preserved moments. Records that no longer correspond to any reachable reality. At the edge of the observable universe, this imbalance becomes absolute. We see galaxies whose light is only just reaching us. But even at the moment that light arrives, the galaxies themselves are already beyond contact. Space has expanded too much. Time has intervened too thoroughly. These objects are visible but causally lost. We can measure their properties. We can trace their histories. We can infer their physics. We can never influence their futures. This is not a failure of technology or ambition. It is a property of space-time itself. Light crosses expanding space because it is woven into space-time structure. Matter must fight that structure. Signals must obey it. This asymmetry defines the universe we inhabit. Observation extends far beyond interaction. Knowledge outruns agency. Understanding arrives without the possibility of response. Even if another civilization exists within one of these distant galaxies, the same rule applies. Their light may reach us, ours will never reach them. Two intelligences could become mutually observable without ever becoming mutually aware. The universe allows awareness without reciprocity. This is why the cosmos feels simultaneously rich and unreachable, full of detail yet closed to contact. What we call the universe is therefore not a shared arena. It is a collection of isolated timelines connected only by one-way signals. To understand how deep this isolation runs, we must examine the rule that governs all movement and communication, the ultimate speed limit of reality. The one constraint that no form of matter or information can overcome, the speed of light. Every attempt to cross the universe runs into the same barrier. Not a wall, not resistance, a limit. The speed of light is not simply the fastest thing we know, it is the fastest thing that can exist. This limit is woven into the structure of space-time itself. It governs how cause leads to effect. It defines which events can influence one another and which remain forever separate. Nothing with mass can reach this speed. The closer it gets, the more energy is required until the demand becomes infinite. Acceleration does not fail gradually. It stops completely. This is not a technological constraint. It is a geometric one. Time slows, length contracts. Momentum grows without bound. The universe resists violation by design. Because of this, no signal can outrun light. No message can arrive before its cause. No shortcut can bypass delay without breaking the logic of reality. This is where many speculative ideas emerge. Wormholes, warp drives, exotic space-time geometries. They appear to offer ways around the limit, but each requires conditions that have never been observed. Negative energy densities, stable configurations of matter that violate known constraints, control over space-time itself. In every case, the mathematics allows possibility only at the cost of physical plausibility. As far as evidence shows, the universe enforces its speed limit absolutely. Even if such mechanisms were real, they would not solve the deeper problem. The universe is expanding. Space itself stretches between distant regions. At large enough separations, expansion carries objects apart faster than light can traverse the growing gap. No amount of speed can compensate for this because nothing moves faster than the space it occupies. This means that even light cannot connect everything. There are regions of the universe from which light emitted today will never reach us. There are signals we send now that will never arrive anywhere meaningful. They will simply be carried outward, diluted into irrelevance. This turns the speed of light from a challenge into a verdict. It declares which futures can be shared and which cannot, which regions belong to the same causal story and which are forever disconnected. At human scales, this limit feels generous. At cosmic scales, it is brutally restrictive. Travel becomes futile long before energy is exhausted. Communication fails long before meaning can be exchanged. Presence becomes impossible even when visibility remains. The universe does not forbid motion. It confines relevance. Within small regions, light speed is more than sufficient. Within galaxies, it defines delay but not disconnection. Between clusters, it becomes a barrier that no effort can overcome. This is why the universe cannot function as a single interactive whole. It is not a network. It is a patchwork. Local regions evolve together. Distant regions evolve alone. The speed of light ensures that this fragmentation is permanent, and yet even this is not the full story, because separation does not only arise from how fast information travels, it also arises from when that information exists. The next barrier is not speed, it is timing. Even if distance could be reduced, and even if speed were no longer a barrier, contact would still face a deeper problem. Timing. The universe does not unfold all at once. It evolves in phases paced by processes that operate over millions and billions of years. Stars ignite and fade. Galaxies assemble and disperse. Conditions that allow complexity appear briefly, then vanish. Civilizations, if they arise, must fit within these narrow intervals. This creates what can be called a civilization window, a period during which a planet remains stable. A star provides steady energy. Chemistry has time to organize into biology. Intelligence emerges before conditions deteriorate. These windows are not synchronized. One civilization may arise early in cosmic history when galaxies were dense and violent. Another may appear much later in a quieter universe shaped by expansion and isolation. Both can exist in the same universe governed by the same physical laws, yet separated by tens or hundreds of millions of years. From the perspective of scale, this separation is absolute. Signals sent by an early civilization may cross space long after that civilization has vanished. Messages arriving from a distant world may describe a reality that no longer exists. The overlap required for two civilizations to exchange information is vanishingly small. They must be close enough in space. They must exist at the same time, and they must persist long enough for signals to travel both ways. This alignment is rare. Even within a single galaxy, the lifetimes of stars vary enormously. Some burn for millions of years, others shine steadily for tens of billions. Planetary systems form, evolve, and destabilize on different schedules. Life itself adds further uncertainty. Complex life may require long periods of stability. Technological intelligence may emerge briefly, then disappear through extinction, self-destruction, or environmental change. The window during which a civilization broadcasts or listens may be short compared to cosmic timescales. Scale magnifies all of this. As distance increases, the time required for communication increases with it. A signal sent across the galaxy may take tens of thousands of years to arrive. Across intergalactic space, millions or billions. By the time a message reaches its destination, the sender's civilization may be unrecognizable or gone. By the time a reply could return, the original receiver may have vanished as well. This is not a failure of intelligence or intention. It is a consequence of temporal mismatch. Civilizations do not line up like synchronized clocks. They flicker on and off across cosmic history, separated by long stretches of silence. From this perspective, the universe may be rich with life and still appear empty. Not because no one is out there, but because no one is out there at the same time. Time dilution turns distance into more than separation. It turns it into misalignment. Two cultures could occupy nearby regions of space and still miss each other entirely. Their moments of awareness pass like ships at night, never overlapping. This reframes the question of contact. The challenge is not simply sending a signal far enough. It is sending it at the right moment and receiving it before either side changes beyond recognition. Scale stretches these moments thin. As the universe ages, expansion increases isolation. As stars exhaust their fuel, stable habitats become rarer. The windows narrow. In this sense, the universe is not hostile to life. It is indifferent to coordination. It allows complexity to arise locally briefly without guaranteeing overlap elsewhere. Understanding this reveals why the universe feels quiet even if it is not empty. Silence does not require absence. It requires poor timing, and when scale governs both space and time, poor timing becomes the default condition. This is why contact is not merely unlikely. It is structurally disfavored, and this leads to a deeper realization. The universe does not merely separate places, it separates histories. When distance, speed, and timing are considered together, a single pattern emerges. Isolation is not an accident, it is the default state of the universe. This is the cosmic isolation problem. It does not rely on assumptions about life intelligence or intention. It follows directly from the structure of space-time itself. Distance separates regions. The speed of light limits exchange. Expansion accelerates separation. Time misaligns histories. Each factor alone would complicate contact. Together they make it extraordinarily rare. On small scales, these effects are negligible. Within a planetary system, interaction is easy. Within a galaxy, it is delayed but possible. Beyond that, the universe begins to fragment. Intergalactic space introduces separation measured not just in distance but in delay. Signals lose relevance before they arrive. Movement becomes symbolic rather than practical. Causality stretches thin. A still larger scale's expansion dominates. Galaxies are carried apart not because they are moving through space, but because space itself grows between them. No engine can counter this. No trajectory can avoid it. Once a region crosses a certain threshold, it leaves the shared future of everything else behind. This creates a universe composed of causal islands. Within each island, matter can interact, histories can intertwine, and futures can be shared. Between islands, connection fades until it disappears entirely. The key insight is this: the universe does not fail to connect itself. It is not incomplete or unfinished. It is functioning exactly as its geometry dictates. Isolation is not imposed by hostility. It is imposed by scale. This challenges a deeply rooted expectation. We tend to assume that if something exists, it should be reachable in principle, that with enough time or technology contact is inevitable. The universe does not support this assumption. Most regions of reality are not just difficult to reach. They are unreachable by definition. This is why speculation about universal networks, galactic communities, or cosmic coordination consistently runs into the same wall. Not because such ideas are imaginative, but because they conflict with how causality behaves on large scales. The cosmic isolation problem does not say that life is rare, it says that overlap is rare. Even if intelligent civilizations are common, they are scattered across space and time in ways that prevent interaction. Each one inhabits its own causal neighborhood, bounded by horizons it cannot cross. From within such a neighborhood, the universe appears quiet. Signals fade into noise. Responses never arrive. Silence stretches on. This silence does not imply emptiness. It implies disconnection. Understanding this reframes the meaning of cosmic loneliness. Loneliness does not arise because the universe lacks others. It arises because the universe prevents most others from ever meeting. Scale ensures that stories unfold separately, that outcomes diverge, that awareness remains local, and yet this isolation is not total. Within each causal island, connection is possible. History can accumulate, meaning can persist. The universe does not deny relationship, it limits its scope. To grasp the true consequences of scale, we must look at how these limits play out in practice. not in theory but in the mechanics of signaling itself, how messages are sent, how they spread, and why they almost never meet. This is where isolation becomes measurable, not as a feeling but as a physical outcome. The failure of signals to converge. Sending a signal into the universe feels simple. A burst of energy, a pattern encoded in waves, a message released into space expanding outward in all directions. In practice, this simplicity hides a cascade of constraints. A signal does not travel as a beam aimed at a destination. It spreads, its energy dilutes with distance. What begins as a focused transmission becomes a thinning shell growing weaker with every passing light year. This dilution is relentless. Double the distance and the signal's strength drops dramatically. Multiply the distance by thousands or millions and even the most powerful transmission fades into background noise. At interstellar scales, this is already a challenge. At intergalactic scales, it becomes decisive. A civilization attempting to announce its presence must overcome not only distance but decay. Energy spreads, interference accumulates. Cosmic background radiation fills space with noise that grows more significant as signals weaken. Even if a signal remains detectable, direction becomes a problem. The universe is vast. Targets are unknown. Broadcasting blindly means most signals pass through empty space, never intersecting with a receiver. A message aimed at a galaxy may miss every habitable system within it simply because of geometry. Receiving is no easier. A civilization must be listening at the right frequency, at the right time, in the right direction. With the right sensitivity, miss any one of these conditions and the signal passes unnoticed. This is not a matter of carelessness or lack of effort. It is a matter of probability. As scale increases, the odds collapse. Consider timing. A signal may pass through a star system millions of years before any technology capable of detecting it exists, or millions of years after such technology has disappeared. The universe does not wait for synchronization. Even within a single galaxy, signals do not linger. They cross vast regions quickly in cosmic terms, but slowly relative to the lifespan of civilizations. They do not hover. They do not repeat unless deliberately designed to do so, and repetition carries its own costs. Sustained broadcasting requires energy over long periods. It assumes stability, intent, and continuity. Few systems remain unchanged long enough to support such commitment. Natural processes add further distortion. Interstellar and intergalactic media scatter and absorb radiation. Magnetic fields alter polarization. Relative motion shifts frequencies through Doppler effects. What arrives is not what was sent. At large distances, reconstructing the original message becomes increasingly uncertain. Information degrades, meaning dissolves. This is why the universe does not function like a communication network. Networks rely on nodes, paths, and feedback. The cosmos provides none of these reliably at large scales. There is no routing, no acknowledgement, no shared protocol. Signals do not converge. They disperse. Two civilizations could broadcast for millions of years and never intersect. Their signals expand into space like ripples on an ocean that never meet. From this perspective, silence is expected, not because no one speaks, but because voices fade before they overlap. The failure of signals to meet is not evidence of absence. It is evidence of scale operating as designed. Distance stretches, signals thin. Time misaligns sender and receiver. Expansion carries messages away from relevance. What remains is a universe where communication is local by necessity. Within small regions, signals cross easily. Across larger ones, they struggle. Beyond a certain point, they are effectively lost. This reveals a deeper truth. The universe does not prevent expression. It prevents coordination. Each civilization, if it exists, speaks into its own expanding horizon. Most of what it sends will never be heard. Most of what it hears will never be answered. Understanding this transforms how silence should be interpreted. Silence is not a mystery to be solved. It is an outcome to be expected, and it forces a final shift in perspective. Perhaps the universe is not quiet because it lacks voices. Perhaps it is quiet because every voice is speaking into a different sky. When communication fails and signals disperse, a subtle transformation takes place. The universe stops behaving like a single shared environment. It fractures into countless local realities. Each observer inhabits a local universe. This is not different cosmos with different laws. Physics remains the same everywhere. What changes is access. A local universe is defined by what can be reached, influenced, and responded to within a finite time. It is bounded by horizons, delays, and expansion. Inside it, cause and effect still function together. Outside it, events unfold independently. From within such a region, reality feels complete. Stars rise and set. Galaxies drift slowly across the sky. Cosmic background radiation fills space evenly. The universe appears coherent and whole, but this coherence is local. Another observer far away in space or time inhabits a different local universe. They see a different sky. They receive light from different galaxies. Their observable structures are not the same as ours. Even the history of the universe they reconstruct will differ. Some galaxies we observe never appear in their sky. Some structures they map are already beyond our horizon. Each perspective assembles a different cosmic story from the light that happens to arrive. There is no privileged viewpoint. No location in the universe sees everything. No observer can access the full structure at once. Every map is partial, shaped by position and era. This breaks a common intuition. We often imagine the universe as a single object that exists all at once, with observers sampling different parts of it. In reality, observers sample different versions of the universe. Not versions in the sense of disagreement or illusion. Versions in the sense of causally distinct subsets of the same reality. This distinction matters. It means that there is no universal present moment, no global now that binds all regions together. Time slices differ across space and access to them differs as well. Two civilizations could both study cosmology with perfect precision and still describe different universes. Their equations would match, their constants would agree, but their skies would not. What one can observe, another cannot. What one considers ancient history, another has not yet seen. What one believes lies beyond reach may still influence the other. Each local universe carries its own limits. Within those limits, meaning accumulates. History matters. Prediction works. Memory persists. Beyond them, relevance dissolves. This is why the idea of a universal conversation fails. There is no single stage where all observers gather. There is no shared timeline where all signals converge. There is no cosmic meeting place. Instead, there are countless overlapping but non-identical regions, each internally coherent, each externally isolated. Local universes overlap partially. They share some history, some structures, some light. But as distance and time increase, the overlap shrinks. Eventually, it disappears entirely. From that point on, two regions belong to the same cosmos but not the same story. This reframes isolation once again. Isolation is not loneliness imposed on a single observer. It is multiplicity without convergence. The universe does not host one narrative. It hosts many unfolding in parallel, rarely intersecting. Each civilization, if it exists, grows inside its own local universe. Its discoveries are shaped by what its sky reveals. Its expectations are shaped by what it can reach. The broader universe may be vast beyond measure, but lived reality is always smaller, defined by horizons, defined by delay, defined by what can still answer back. Understanding this makes one thing clear: the universe is not meant to be shared in full. It is meant to be experienced locally, and as time passes, those local experiences drift farther apart. The next step in this journey looks forward, not outward, because the future of the universe does not increase connection, it reduces it. If the universe already limits connection, the future tightens those limits further. Expansion is not slowing down, it is accelerating. Dark energy stretches space at an increasing rate, quietly reshaping what can ever remain connected. This acceleration does not tear structures apart locally. Galaxies, stars, and planets remain bound where gravity is strong enough, but it redraws the boundaries between regions. As time moves forward, fewer places remain within reach. Galaxies outside our local group are already slipping away. Their light still arrives, but their futures do not intersect with ours. With each passing billion years, more of the universe crosses the threshold from distant to unreachable. This process is irreversible. Once expansion carries a region beyond the causal horizon, no signal sent afterward can ever arrive there. No reply can return. The shared future ends. From a cosmic perspective, the universe is not opening. It is closing, not collapsing inward, but fragmenting outward. In the far future, this effect becomes dominant. Observers inside a bound group of galaxies will see fewer and fewer external structures. Distant clusters will fade as their light stretches beyond detectability. The cosmic web will dissolve into darkness. Eventually, the night sky will grow quiet in a literal sense. Only the merged remnant of the local group will remain visible. All other galaxies will vanish beyond the horizon, leaving no trace that they ever existed. For those future observers, the universe will appear small and static. Cosmic expansion will be invisible. The evidence of a once vast structured universe will be lost. This is not speculation. It follows directly from the equations governing expansion. Scale does not merely separate the present, it erases the past. Structures that once shaped cosmic evolution will become unobservable. Histories that once overlapped will become inaccessible. Knowledge itself will contract. From within a future local universe, the idea of other galaxies may seem unnecessary. The sky will offer no hint of them. Physics will still be correct but incomplete. This highlights a crucial asymmetry. The universe allows early observers to see far more than late ones. Access decreases with time. Connection decays. In this sense, we live at a privileged moment. Not because we are special, but because the universe is young enough to still be visible. Because light from distant regions has not yet been stretched beyond reach. Because cosmic history remains partially accessible. This window will not remain open. As expansion continues, isolation becomes the norm rather than the exception. Local universes become smaller, shared reality fragments further. From this perspective, the universe is not simply large and quiet, it is becoming quieter. Every generation that follows will inherit less connection than the one before. Fewer galaxies to observe, fewer structures to map, less shared future beyond their immediate surroundings. Scale is not a static backdrop, it is an active force shaping destiny. It determines not only what exists, but what can ever be known. Not only where things are, but whether they can matter to one another at all. In the end, the universe trends toward isolation, not as a catastrophe, not as a collapse, but as a natural consequence of how space and time evolve together, which leaves one final question. If connection becomes rarer with time, what does that mean for meaning itself? That question does not point outward. It points inward, toward the small regions where connection still survives, and toward the quiet responsibility of being aware while the window remains open. When all constraints are placed together, the universe reveals a calm but uncompromising truth. Connection is not the default condition of reality. It is the exception. Distance limits reach. Time limits overlap. Expansion limits shared futures. None of these act with intent. They are not barriers erected against meaning, they are simply how the universe works. From within this framework, silence no longer appears mysterious. It becomes expected. A universe can be rich with structure and still quiet. It can host countless stars and still prevent conversation. It can allow life to arise repeatedly while ensuring that most of it never meets. The absence of contact does not require the absence of others. It requires only scale. This reframes a question that has echoed for decades. Where is everyone? The more precise question may be different. How many were never able to reach anyone else? Each civilization, if it exists, grows inside a narrow causal pocket. It observes what its sky allows. It acts within what its horizon permits. Beyond that boundary, reality continues without reference to its choices. There is no universal audience, no shared stage where all stories converge, no cosmic moment when everything aligns. Instead, there are countless local narratives unfolding independently. Some may rise to awareness, some may not. Most will remain forever unknown beyond their own region. This is not a failure of the universe. It is its equilibrium, a cosmos built for local complexity rather than global coordination, a structure that preserves diversity by preventing convergence, a system where meaning emerges briefly locally and without guarantee of continuation elsewhere. From this perspective, the quiet sky is not empty. It is full of untold stories that never intersect. This realization shifts the emotional weight of scale. The universe is not cold because it is vast. It is calm because it is divided. Within each division, events matter intensely. Lives unfold. Histories accumulate. Choices have consequence. Beyond those divisions, nothing listens. And that may be precisely why awareness, when it appears, is so rare and so fragile. The universe does not demand that it be known. It does not ensure that understanding spreads. It simply allows small regions where understanding can arise at all. We inhabit one of those regions, a local universe with a shared past, a limited future, and a shrinking horizon, a place where connection still functions for now, where signals can still meet, where stories can still overlap. This does not make our position central, it makes it temporary. The true consequence of scale is not insignificance, it is responsibility. Because within a universe that increasingly isolates its parts, meaning survives only where connection still exists. Here, now, before the distances grow larger, the delays grow longer, and the sky grows quieter still. That is the quiet reality the universe offers, not a promise of contact, but a brief window in which awareness can look outward, understand the limits, and recognize how rare that opportunity truly is. In the end, the universe does not leave us with a riddle. It leaves us with a condition, a reality where distance outpaces effort, where time misaligns histories, where expansion ensures that most futures never overlap. This is not a universe built for gathering. It is a universe built for separation, and yet separation is not the same as meaninglessness. Within a narrow range of scale, connection survives. Atoms bind. Chemistry remembers. Life persists long enough to ask questions. Intelligence arises long enough to notice how fragile its reach truly is. That narrow range is where we live, not at the center of anything, not at a privileged location, but at a moment when the universe is still young enough to be seen, and small enough to be partially shared. We exist during a brief cosmic interval. Galaxies are still visible. The cosmic web can still be mapped. Light from distant eras still arrives with information intact. The sky still tells a story larger than our own. This will not always be true. As time advances, horizons shrink, connections dissolve, evidence fades. Future observers will inherit a quieter universe not because reality has emptied, but because access has closed. They will look out and see less, know less, and infer less about what once existed beyond their reach. We are not wiser because we are superior. We are simply early enough to see. This places scale in its final context. The universe is not asking to be crossed. It is asking to be understood while understanding is still possible. Connection does not need to be cosmic to matter. It needs to be local, sustained, preserved, in a reality where most things never meet. Every meeting counts. Every signal received is a victory over distance. Every shared history is an exception carved out of scale. Every act of understanding is temporary, fragile, and rare. The universe will continue to expand. Isolation will increase. Local universes will drift farther apart. But for now, the window remains opened, and within that window awareness exists, looking outward, recognizing the limits, and understanding that meaning does not come from reaching everything. It comes from recognizing what can still be reached. Here, together, before the universe grows quieter still. There is a quiet assumption hidden inside every scientific question that if something exists, it can eventually be confirmed. Throughout human history, this assumption has usually held mountains could be climbed, oceans could be crossed, invisible forces could be measured once instruments became precise enough. Ignorance felt temporary. The universe breaks this pattern, not because it hides information, but because it places most of reality beyond verification by design. When we look into the sky, we see galaxies stretching to the edge of visibility. We measure their motion, we map their distributions, we reconstruct their history with remarkable accuracy, and yet everything we observe represents only a fraction of what exists. Beyond the observable horizon lies more universe than we will ever see, not dimmer, not harder to detect, but fundamentally unreachable. This creates a distinction that is easy to overlook. There is what we have observed, there is what is observable in principle, and there is what exists regardless of observation. These categories are not the same. Much of modern cosmology operates in the space between them. We infer the presence of dark matter without seeing it directly. We describe dark energy through its effects rather than its substance. We model regions of the universe that no signal will ever bring us information from. None of this is failure. It is precision under constraint. The universe allows us to see enough to understand its structure, but not enough to confirm it everywhere. It offers patterns, not completeness. Consistency, not total access. This places science in an unfamiliar position. In most fields, uncertainty shrinks as data accumulates. In cosmology, some uncertainties never disappear. They are not gaps waiting to be filled. They are boundaries that cannot be crossed. We live inside a universe that does not permit full verification. No experiment can be repeated at cosmic scale. No observation can sample regions beyond our horizon. No instrument can reach outside the shared causal past. We have one universe, one history, one vantage point. Everything we know about the whole is inferred from a part. This does not make cosmology speculative, it makes it asymmetrical. Some truths can be tested directly, others can only be supported indirectly, and some may always remain unconfirmed even if they are correct. This challenges a deeply held intuition, that reality must be fully knowable if we are clever enough, that ignorance is merely a temporary lack of tools, that understanding converges toward completeness. The universe does not promise this. It allows understanding to grow, but only within limits set by scale time and causality. Beyond those limits, knowledge becomes structural rather than empirical. We do not verify the universe as a whole, we reconstruct it, from fragments of light, from statistical patterns, from consistency across what can be seen. This raises a question that science rarely asks directly. If most of reality can never be confirmed, what does it mean to know anything at all? The answer does not lie in resignation. It lies in redefining what knowledge means inside an incomplete universe. That is the journey that follows, not toward more data, but toward understanding the boundaries of confirmation itself. In everyday life, knowing and inferring feel nearly the same. If you see smoke, you know there is fire. If an object falls, you know gravity is acting. Cause and effect sit close enough together that certainty feels immediate. In cosmology, this closeness disappears. Much of what we claim to know about the universe is not observed directly. It is inferred. This distinction is not semantic. It is foundational. Direct knowledge comes from interaction. You measure a signal. You repeat the observation. You confirm it under controlled conditions. Inference works differently. You observe an effect. You rule out alternatives. You identify the simplest explanation that fits all available data, and you accept that explanation provisionally, knowing it may never be observed on its own. This is how we know the universe contains far more matter than we can see. Galaxies rotate too fast for their visible mass. Clusters hold together more tightly than gravity alone should allow. Light bends more than expected as it passes through empty space. From these effects we infer dark matter. We do not see it. We do not touch it. We do not detect it directly, but the universe behaves as if it is there. The same is true for dark energy. The expansion of the universe is accelerating. Galaxies drift apart faster over time, not slower. No known form of matter or radiation can explain this behavior, so we infer a component of reality that acts against gravity on the largest scales. We name it, we model it, but we do not observe it in isolation. These inferences are not guesses, they are constrained conclusions drawn from consistent, repeatable patterns. They survive because every alternative explanation fails more severely, yet they reveal a crucial limit. Some of the most important components of the universe are known only by their influence, not by their presence. This asymmetry grows stronger with scale. The larger the structure, the harder it is to observe directly. The earlier the epoch, the fewer signals remain. The farther the region, the more inference replaces measurement. Even the overall shape of the universe is inferred. We measure local geometry. We examine cosmic background radiation. We track large-scale structure. From these pieces, we extrapolate the global properties of space, flatness, curvature, topology. But we do not survey the whole. We assume uniformity beyond what we can see, not because it is proven everywhere, but because it is the only assumption that preserves consistency. This is a subtle but profound shift. In most sciences, inference shrinks as data grows. In cosmology, inference expands with understanding. The better we map what is observable, the more clearly we see what will never be directly observed. Knowing in this context does not mean verifying every instance. It means identifying rules that remain stable across everything we can access. We do not know that dark matter exists everywhere. We know that every place we can measure behaves as if it does. We do not know what lies beyond the observable universe. We know that the same physical laws explain everything within it without contradiction. This is not weakness, it is adaptation. Cosmology adjusts its definition of knowledge to match the structure of reality. It accepts that some truths are global even when confirmation is local. Inference becomes the bridge between observation and totality. Without it, cosmology collapses into silence beyond the horizon. With it, the universe becomes intelligible though never complete. Understanding this difference is essential, because the universe does not reward certainty, it rewards consistency. And in an incomplete universe, consistency is the closest thing to knowing we will ever have. In most sciences, uncertainty can be reduced by repetition. You run the experiment again. You change the conditions. You compare outcomes across multiple trials. Patterns emerge, errors cancel, confidence grows. Cosmology does not have this luxury. We do not study many universes. We study one set of initial conditions. One expansion history, one realization of physical law playing out across space and time. This creates a fundamental constraint known as the one-sample universe problem. Every conclusion about the universe as a whole is drawn from a single example. There is no control group, no alternate run, no way to reset the initial state and observe what changes. The Big Bang happened once. Cosmic inflation, if it occurred, unfolded once. The distribution of galaxies we observe is one outcome among countless theoretical possibilities. When we say the universe is flat or expanding or dominated by dark components, we're not describing an average across many cases. We are describing the behavior of a single realization. This does not make the conclusions invalid. It changes what they mean. In a laboratory, laws are tested by variation. In cosmology, laws are inferred by coherence. We ask whether one set of assumptions explains everything we see without contradiction. If it does, we accept it not because it is proven universally, but because it is internally stable. This is why cosmology relies so heavily on simplicity. The simplest model that fits all available data is favored not because nature must be simple, but because complexity cannot be independently verified. Additional assumptions cannot be tested if there is only one universe to examine. Even statistical tools behave differently at cosmic scale. When cosmologists speak of probability, they do not mean frequency across many universes. They mean likelihood given one observed outcome and a theoretical framework. This distinction is subtle but critical. We cannot say how likely our universe is compared to others because we have no access to others. We can only say whether our models reproduce what we observe inside this one. This limitation becomes most apparent when discussing the early universe. Conditions shortly after the Big Bang shaped everything that followed. Small fluctuations grew into galaxies. Tiny asymmetries became large-scale structure. We observe the result. We do not observe the process unfolding multiple times. Every inference about the beginning is therefore indirect. We work backward from the present constrained by physics we can test locally. We assume those laws applied universally because nothing within observation contradicts that assumption. But the assumption itself cannot be verified beyond our horizon. This does not undermine cosmology. It defines it. Cosmology is not the science of repeating experiments. It is the science of reconstructing a singular history. Its strength lies in consistency across scales, in the fact that the same equations describe particle interactions and cosmic expansion, in the fact that predictions made decades ago match observations gathered much later. Yet the one-sample problem never disappears. There will always be questions we cannot answer by comparison. Was our universe typical? Could it have been different? Are its properties rare or common? These questions may be meaningful, but they are not testable in the usual sense. This forces a kind of intellectual humility. We can describe how the universe behaves. We can model its structure with extraordinary precision, but we cannot step outside it to see whether it could have been otherwise. We live inside the only sample we will ever have. And that means that some aspects of reality will always be known from the inside, never confirmed from the outside. Understanding this does not weaken cosmology. It clarifies its boundaries, because the deepest limits of knowledge do not come from ignorance or lack of effort. They come from the fact that the universe gives us only one chance to observe it, and from that single chance we must infer the whole. In cosmology, horizons are often described as limits of vision, lines beyond which light has not yet arrived. But this description is incomplete. Cosmic horizons are not just boundaries of sight. They are boundaries of verification. Everything beyond a horizon is not merely unseen. It is untestable. No signal from those regions can reach us now. No experiment conducted here can influence them. No observation made tomorrow will ever change that. This transforms the horizon into a permanent epistemic boundary. Inside it, physics can be checked. Predictions can be compared to data. Models can be refined or rejected. Outside it, none of this is possible. We may extrapolate. We may infer, but we cannot confirm. This distinction is crucial. There is a difference between what is unknown and what is unknowable. An unknown fact lies beyond current measurement, but may be reached with better instruments or more time. An unknowable fact lies beyond causal contact entirely. Much of the universe belongs to the second category. Regions beyond the observable horizon may follow the same physical laws. They may contain similar structures, galaxies, or entirely different arrangements of matter. We cannot check. No improvement in technology can change this. No future telescope will peer past a causal boundary. No clever experiment will retrieve information that space-time itself forbids from arriving. This makes cosmology unlike any other empirical science. In geology, we cannot witness the formation of a mountain, but we can examine its layers. In biology, we cannot observe ancient evolution directly, but we can analyze genetic records. In cosmology, some regions leave no record at all. They exist without trace. Even the assumption of uniformity so central to cosmology rests on this boundary. We assume the universe is homogeneous and isotropic on large scales. We test this assumption wherever observation allows. Within that range, it holds remarkably well. Beyond it, we extend the assumption not because we know it is true, but because abandoning it would destroy explanatory power without offering testable alternatives. This is a rational choice, not a proof. It reflects a fundamental compromise between knowledge and reach. Horizons also fracture history. Light from different distances corresponds to different epochs. As we look farther, we look deeper into the past. Beyond a certain point, no light remains to carry information forward. What happened there cannot be reconstructed from observation alone. At best, it can be constrained indirectly through its effects on later eras. This is why early universe cosmology is built on traces rather than records. Fluctuations in background radiation, statistical patterns in galaxy distribution, subtle correlations that survive expansion. They are fossils, not witnesses. Beyond the horizon, even fossils disappear. This introduces a permanent asymmetry in our understanding. We can describe the universe inside our horizon with increasing accuracy. We can test models against data and reject those that fail. But the universe as a whole will always include regions that remain beyond confirmation, not hidden, not protected, simply unreachable. Recognizing horizons as knowledge boundaries shifts the meaning of cosmological truth. A statement about the universe is not required to be verified everywhere to be meaningful. It must be verified everywhere verification is possible. Beyond that, truth becomes conditional, not arbitrary, but bounded. The universe does not grant omniscience. It grants partial access. Within that access, science works extraordinarily well. Beyond it, science becomes inference guided by consistency, not observation. This is not a weakness of method. It is a reflection of the universe's structure. Reality extends farther than confirmation allows, and no amount of curiosity can collapse that distance. Understanding this boundary is essential, because it explains why some questions remain permanently open, not because they are ill-formed, but because the universe itself does not permit their answers to arrive. This is what it means to live inside an incomplete universe, not one lacking explanation, but one that withholds verification beyond a horizon that cannot be crossed. It is tempting to believe that explanation converges toward completion, that with enough data, enough precision, and enough time, every mystery yields. That science advances by closing gaps until none remain. Cosmology resists this narrative, not because its questions are poorly formed, but because its subject is larger than the conditions required for full explanation. To explain something completely is to test it under all relevant conditions, to vary inputs, to observe outcomes, to confirm that no hidden factors remain. The universe does not allow this. We cannot vary its initial conditions. We cannot isolate its parameters. We cannot repeat its history under controlled changes. Even a hypothetical theory of everything would face this constraint. Such a theory might unify forces. It might describe particles, fields, and space-time within a single framework. It might predict the behavior of everything we can observe with extraordinary accuracy, and yet it would still operate inside an incomplete evidential field. It could tell us how the universe behaves. It could not confirm why this universe exists rather than another. Many of the deepest cosmological questions sit precisely at this boundary. Why do physical constants take the values they do? Why does the universe have the geometry it has? Why did expansion begin the way it did? These are not questions about mechanism. They are questions about selection, and selection requires comparison. Without multiple universes to compare, explanations drift toward inference rather than confirmation. Models become internally consistent but externally unverifiable. This does not render them meaningless. It defines their scope. An explanation can be complete within a model, and still incomplete with respect to reality as a whole. Cosmology therefore operates with a different notion of sufficiency. A theory is accepted not because it explains everything that could exist, but because it explains everything that can be observed without contradiction, using the fewest assumptions. This is a pragmatic standard, not an absolute one. It acknowledges that some aspects of reality may never be reduced further, not because they are mystical, but because they are structurally inaccessible. Consider cosmic inflation. Inflationary models explain the large-scale uniformity of the universe. They account for observed fluctuations, They predict statistical patterns that match data with remarkable precision. But inflation itself may never be observed directly. Its details may vary beyond our horizon. Its deeper cause may lie in regimes forever outside empirical reach. The explanation works. Verification remains partial. The same is true for dark energy. We describe its effects with increasing accuracy. We constrain its properties. We test competing models. But its underlying nature may never be isolated experimentally. It may remain a parameter rather than a substance. This reveals a crucial insight. Explanation does not require exhaustion. Understanding how something behaves within all accessible conditions may be the most that reality allows. Demanding more may be demanding what cannot exist. This does not diminish science. It redefines its ambition. Science is not the conquest of all possible truths. It is the construction of reliable knowledge within the limits imposed by nature. In cosmology, those limits are unusually sharp. They are not technical. They are not temporary. They are built into space-time itself. As a result, the universe may never be fully explained in the sense of total verification. There may always remain truths that are consistent, necessary, and unconfirmable. This is not failure. It is alignment with reality. A complete explanation would require complete access. The universe does not grant that access. Instead, it offers coherence. Patterns that repeat wherever we can look. Laws that hold across every scale we can test. Predictions that succeed within the observable domain. Within those bounds, explanation is powerful. Beyond them, explanation becomes conditional. Not wrong, not speculative, but incomplete by necessity. Understanding this distinction is essential, because it marks the difference between a universe that resists explanation and a universe that defines the limits of explanation itself. We do not fail to fully explain the universe. We discover that full explanation was never possible to begin with. Certainty is a powerful expectation. In everyday science, it grows naturally from repetition. Measure the same effect often enough and confidence solidifies. Disagreement narrows. Error bars shrink. Cosmology does not converge this way. At the largest scales, uncertainty does not fade with time. It stabilizes. This is not because measurements are poor. Modern cosmology is extraordinarily precise. We measure cosmic background radiation to parts per million. We map galaxy distributions across billions of light years. We track expansion with multiple independent methods. Yet precision does not equal certainty. Many cosmological conclusions are not fragile. They are robust across datasets, instruments, and techniques, but they remain conditional on assumptions that cannot be tested globally. This creates a different kind of confidence. Not absolute certainty, but constrained plausibility. When cosmologists state that the universe is flat, they do not mean perfectly flat everywhere forever. They mean that within observational limits, curvature is indistinguishable from zero. Beyond those limits, curvature may vary in ways that cannot be checked. When they describe the composition of the universe, they do not claim to have inventoried all of reality. They describe the components required to explain observed behavior within the accessible domain. This is a subtle but important distinction. Cosmic certainty is local. It applies within horizons, within epochs, within the region where evidence can arrive. Outside those bounds, certainty gives way to consistency. A model is trusted not because it is proven everywhere, but because it survives every test that can be performed. It fails nowhere that failure could be detected. This is the strongest form of knowledge available in an incomplete universe. Probability plays a different role here as well. In laboratory science, probability reflects ignorance about outcomes that could in principle be repeated. In cosmology, probability often reflects ignorance about conditions that cannot be sampled again. We assign likelihoods to parameters not because we expect to observe many universes, but because we must quantify uncertainty within one. This leads to an uncomfortable realization. Some cosmological statements may never become more certain than they are now. Not because data will stop improving, but because improvement cannot break through causal boundaries. Uncertainty does not always signal weakness. Sometimes it signals the edge of reach. This challenges a common narrative about scientific progress. Progress is often imagined as a march toward total clarity. But in cosmology, progress frequently reveals where clarity must stop. As measurements improve, we do not eliminate unknowns. We classify them. We learn which uncertainties are technical and which are structural, which gaps can close and which define the horizon of knowledge itself. This classification is itself a form of understanding. Knowing what cannot be known is not defeat. It is orientation. It prevents false confidence. It prevents speculative excess. It keeps explanation anchored to evidence. Cosmology therefore practices a disciplined humility. It does not claim certainty where confirmation is impossible. It does not retreat into doubt where consistency is strong. It occupies the narrow space between. This balance is difficult to maintain. Too much certainty invites overreach. Too little invites paralysis. The universe enforces this balance by design. It allows enough access to discover deep structure. It withholds enough access to prevent closure. Within this tension, cosmological knowledge advances, not toward omniscience, but toward stable understanding under constraint. The limits of cosmic certainty are not obstacles to truth. They are the conditions under which truth remains meaningful. Because in a universe that cannot be fully verified, certainty must be earned, locally defended carefully, and never extended beyond what evidence allows. Understanding this prepares us for the next step, not toward resignation, but toward recognizing what science can still do, even when completeness is impossible. Acknowledging limits does not weaken science, it sharpens it. In an incomplete universe, the role of science is not to claim total access. It is to extract reliable structure from partial information. This distinction matters. Science does not require omniscience to function. It requires consistency, testability where possible, and the discipline to stop where confirmation ends. Cosmology exemplifies this approach. Despite having access to only a fraction of reality, it has revealed deep non-trivial order. The same equations describe atomic interactions and the evolution of galaxies. The same physical constants govern processes across vast differences in scale. Predictions made from early data continue to hold as observations improve. This is not accidental. Even when verification is local, laws can be global. When a rule holds everywhere, it can be tested, and when extending it further introduces no contradictions, science gains justified confidence in its scope. Not certainty everywhere, but reliability everywhere access allows. This is how cosmology builds knowledge. It maps relationships rather than inventories. It identifies invariants rather than exhausts instances. It focuses on what must be true for observed reality to behave as it does. For example, we may never directly observe dark matter particles, but we can constrain their properties so tightly that entire classes of models are ruled out. We can test how they cluster, how they influence structure, and how they interact gravitationally. Even without direct detection, their role becomes increasingly precise. The same applies to early universe physics. We cannot rerun cosmic history, but we can test whether models reproduce the patterns frozen into background radiation galaxy distributions and elemental abundances. When independent lines of evidence converge, confidence grows, not because the universe has been fully accessed, but because the same explanation succeeds repeatedly under different constraints. Science in this context acts like a map maker. A map does not contain every grain of sand. It captures structure, relationships, and boundaries. It is judged not by completeness, but by usefulness and accuracy within its intended domain. Cosmological models function the same way. They do not claim to show all of reality. They show how reality behaves where it can be observed, and how that behavior constrains what lies beyond. This approach also protects science from overreach by clearly identifying which questions are empirical and which are extrapolative. Cosmology avoids turning speculation into assertion. It maintains a separation between what is supported by evidence and what is suggested by coherence. This discipline is crucial. In a universe where verification has hard limits, unchecked speculation can easily masquerade as explanation. Science resists this by demanding that every claim remain tethered to observable consequences, even if those consequences are indirect. As a result, science continues to advance even when completeness is impossible. It refines parameters, it tightens constraints, it eliminates alternatives, it clarifies which features of reality are necessary and which are contingent. Perhaps most importantly, it preserves a shared standard of truth. Even in an incomplete universe, statements can be compared, tested, and debated using common criteria. Agreement is earned through evidence, not authority. Uncertainty is acknowledged explicitly rather than hidden. This is the strength of science under constraint. It does not promise final answers. It promises reliable ones. Within the accessible universe, science works with extraordinary power. Beyond it, science remains cautious, extending models only where consistency allows. This balance is not a compromise. It is an adaptation to the structure of reality itself. The universe does not allow full verification. Science responds by becoming more precise about what it claims. In doing so, it remains effective, honest, and resilient. The question then shifts. If knowledge is necessarily incomplete, how should we live with that incompleteness? Not as a technical issue, but as a feature of understanding itself. Human intuition is shaped by closure. We expect questions to have answers. We expect uncertainty to shrink with effort. We expect understanding to approach completion even if it takes time. An incomplete universe disrupts this expectation. It asks us to accept that some questions remain open not because we lack intelligence, but because reality withholds access. Not every gap is a failure of method. Some are features of scale. This distinction matters for how knowledge is held. In many areas of life, uncertainty signals ignorance. It motivates action. It implies that a solution exists and can be reached. In cosmology, uncertainty often signals a boundary. Beyond that boundary, asking for confirmation becomes meaningless, not because the question is poorly formed, but because no evidence can ever arrive to answer it. Learning to live with this requires a different posture toward knowledge, not resignation, not skepticism, but calibrated humility. This humility does not reject inference. It recognizes its role. It understands that inference is not a weakness in a universe that cannot be fully sampled. It is the only bridge available between observation and totality. Living with incomplete knowledge means distinguishing between levels of confidence. Some statements are directly supported by measurement. Others are strongly inferred from multiple independent effects. Still others are plausible extensions that remain permanently untestable. Treating these categories as equivalent erodes understanding. Separating them preserves it. This separation also protects against two common failures. The first is overconfidence. Extending conclusions beyond evidence creates the illusion of completeness. It turns models into dogma and inference into certainty. The second is paralysis. Refusing to accept any inference that cannot be fully verified collapses knowledge into triviality. It denies structure where structure is evident. An incomplete universe demands a middle path, one where confidence is proportional to access, where claims are scaled to evidence, where the absence of verification is acknowledged without becoming an obstacle to understanding. This approach reshapes how cosmology speaks. It replaces absolute statements with conditional ones. It emphasizes ranges, constraints, and dependencies. It treats explanations as maps rather than mirrors. For the observer, this can feel unsettling. The desire for final answers runs deep. So does the impulse to resolve uncertainty by speculation or belief. But cosmology offers a different lesson. Understanding does not require total access. It requires coherence within limits. Accepting incompleteness does not weaken meaning. It grounds it. It allows us to value what can be known without demanding what cannot. It encourages precision over totality. It favors reliability over reach. This has broader implications. In a universe where most of reality will never be confirmed, certainty becomes local. Knowledge becomes contextual. Truth becomes something approached asymptotically, not possessed absolutely. This is not relativism. The laws we discover are not arbitrary. They hold wherever they can be tested. They predict with extraordinary success. What changes is not truth but expectation. We stop expecting the universe to be fully transparent. We stop expecting explanation to be exhaustive. Instead, we learn to inhabit a reality where understanding is partial but robust, where the map is accurate within its domain, even if the territory extends beyond it. Living with incomplete knowledge is not a philosophical concession. It is a scientific adaptation to scale, and it prepares us for a final realization that the universe does not owe us answers. It offers patterns, it offers consistency, and it offers just enough access for understanding to arise. Nothing more. It is natural to expect the universe to be legible. Human understanding evolved in environments where feedback was immediate. Actions produced visible outcomes. Questions had answers that could be reached by effort, patience, or better tools. Cosmology violates this expectation. The universe does not present itself as a puzzle designed to be solved. It does not adjust its scale to match our capacity for confirmation. It does not guarantee that every pattern it displays can be traced back to an observable cause. This is not indifference in a human sense. It is neutrality. The universe follows its laws without regard for whether they are fully accessible to observers inside it. Reality unfolds according to structure, not expectation. From this perspective, the demand for complete explanation becomes misplaced. The universe does not owe us verification. It does not owe us closure. It does not owe us a final inventory of what exists beyond reach. What it offers instead is consistency. Where observation is possible, behavior aligns with law. Where interaction can occur, cause and effect remain reliable. Where measurement can be repeated, patterns persist. Beyond that, reality continues without obligation to be known. This reframes the relationship between science and the cosmos. Science is not a negotiation with reality. It is an adaptation to it. It develops methods that work where access exists. It refines inference where direct contact ends. It resists the temptation to fill unreachable gaps with certainty. This discipline is essential. Without it, the absence of confirmation invites excess. Speculation expands to replace evidence. Narratives grow where testing cannot follow. Cosmology avoids this by drawing a clear line. It does not deny the existence of what lies beyond observation. It denies the claim that such regions must be fully described. This restraint is not pessimism. It is precision. A universe that does not owe us answers still allows understanding. It simply constrains where understanding applies. Within those constraints, explanation can be deep and transformative. We can trace the origin of elements. We can reconstruct the growth of structure. We can predict the fate of cosmic expansion. These achievements are not diminished by the existence of unconfirmable regions. They are strengthened by recognizing their domain. Accepting this shifts the emotional posture of inquiry. Curiosity no longer demands total resolution. It values coherence over completeness. It recognizes that some questions are meaningful even when answers remain inaccessible. This is not resignation. It is alignment with reality's scale. The universe is not withholding answers out of secrecy. It is extending beyond the reach of verification by necessity. Understanding this prevents a subtle error. The error of assuming that unanswered questions imply hidden mechanisms waiting to be revealed. Sometimes unanswered questions imply boundaries that cannot be crossed. Acknowledging those boundaries does not halt discovery. It channels it. It focuses effort on what can be tested. It refines models where evidence accumulates. It maintains clarity about where explanation ends and extrapolation begins. In this sense, an incomplete universe is not hostile to science. It defines the terms under which science remains honest. Reality is larger than confirmation allows. Science responds by becoming more careful about what it claims. This balance preserves trust. It ensures that knowledge where it exists is earned. It ensures that uncertainty where it remains is explicit. A universe that does not owe us answers still allows meaning to emerge, not from total access, but from disciplined understanding within limits. And this brings the journey to its final point. If reality is only partially confirmable, then knowing enough becomes more important than knowing everything. The question is no longer how to complete the picture. It is how to live responsibly with a picture that will always be incomplete. At some point, the pursuit of completeness must give way to a different question. Not what is everything, but what is enough to understand our place. In an incomplete universe, knowledge is not measured by total coverage. It is measured by stability. What we know about the cosmos does not flicker or collapse under scrutiny. The laws that govern motion, energy, and structure hold wherever they can be tested. The same principles explain the behavior of particles and the evolution of galaxies. Across enormous differences in scale, coherence persists. This is not partial understanding in a weak sense. It is partial understanding in a strong one. We may never confirm what lies beyond the horizon, but what lies within it already reshapes everything we thought we knew. It tells us that space is expanding, that time has depth, that structure emerges from simple rules applied relentlessly over billions of years. These insights do not require total access to be transformative. Knowing enough does not mean closing every question. It means knowing which questions matter where. Within the observable universe, science delivers extraordinary clarity. It predicts phenomena before they are observed. It unifies disparate domains under shared principles. It reveals order where intuition once saw chaos. Beyond that domain, science remains honest about its limits. This honesty is not a weakness. It is a form of intellectual integrity rarely demanded elsewhere. An incomplete universe forces a discipline that few other subjects require. It demands that explanation stop where evidence stops. That inference remain tethered to consistency rather than ambition. That curiosity coexist with restraint. This balance changes how meaning is constructed. Meaning no longer comes from total explanation. It comes from orientation. We understand where we are in time. We understand how fragile complexity is. We understand that awareness arises in narrow windows carved out of vast processes. That understanding is sufficient. It does not answer every conceivable question. It answers the ones that situate us within reality rather than above it. There is a temptation to see incompleteness as loss, as if something essential is missing because it cannot be confirmed. But incompleteness is not absence. It is scale asserting itself. The universe is larger than verification allows. That fact does not diminish what can be known. It defines the context in which knowledge becomes meaningful. Knowing enough means accepting that understanding has edges, not jagged failures, but smooth horizons. Beyond those horizons, reality continues. Within them, explanation holds. This acceptance has a quiet consequence. It shifts the role of the observer. We are not judges of the universe's completeness. We are participants inside a structure that permits partial insight and denies total access. Our task is not to finish the universe conceptually. It is to understand the region we inhabit with clarity, care, and honesty. That is already a profound achievement. The universe does not need to be fully confirmed to be deeply understood. It needs only to be consistent where it can be tested and transparent about where it cannot. In that sense, the universe is not incomplete in a way that frustrates understanding. It is incomplete in a way that protects it. It ensures that knowledge remains grounded, that explanation remains disciplined, and that meaning arises not from total reach but from precise awareness within limits. To live inside an incomplete universe is not to live in ignorance. It is to live in alignment with reality's true scale, and that may be the most complete understanding we can ever achieve. In the end, the universe does not resolve into a finished picture. It remains open at the edges, not because something is missing, but because reality extends beyond confirmation. This is not a flaw in our understanding. It is the condition under which understanding exists. We live inside a universe that can be explored deeply, but never exhausted, where patterns repeat reliably within reach, yet refuse to be verified everywhere, where laws hold with remarkable consistency, even as their full domain remains inaccessible. The desire for closure is human. It reflects a need for completion, for final answers, for certainty that leaves nothing unresolved. The universe does not satisfy this desire. Instead, it offers something quieter and more demanding. It offers coherence without totality, explanation without omniscience, understanding without closure. Within the observable domain, knowledge is not fragile. It does not wobble under new data. It becomes sharper, more precise, more constrained. What changes is not confidence but expectation. We stop expecting the universe to reveal everything. We stop mistaking horizons for failures. We stop assuming that unanswered questions imply hidden doors waiting to be opened. Some doors are not locked. They simply do not exist. The universe is not withholding truth. It is structured in a way that makes some truths unverifiable by necessity. Accepting this does not diminish curiosity. It refines it. Curiosity becomes focused rather than boundless. It seeks depth where access exists. It respects limits where access ends. This is how science remains honest in the face of scale. It does not retreat from what cannot be known. It clearly marks the boundary between evidence and inference. It builds reliable understanding without pretending to completeness. In doing so, it preserves meaning. Meaning does not come from knowing everything. It comes from knowing enough to orient ourselves within reality. We know that the universe has a history, that it evolves, that structure emerges from simplicity, that awareness arises in narrow windows carved out of vast processes. We know that most of reality will never be confirmed, and we know why. These two forms of knowledge coexist without contradiction. The universe remains larger than our reach. Our understanding remains smaller than the universe, and yet within that imbalance clarity emerges. To live inside an incomplete universe is not to accept defeat. It is to accept proportion, to recognize that understanding is not a conquest but a relationship bounded by scale. That knowledge grows not by eliminating mystery but by distinguishing what can be known from what cannot. The universe does not ask us to finish it conceptually. It asks us to understand our position within it accurately. Here, now, inside the limits that make meaning possible. That is not an incomplete achievement. It is the only kind of understanding a universe like this allows.